Hello, everyone. Welcome to another UAA College of Engineering Professional Development Seminar. Our presenter today is Dr. Daisy Huang. Dr. Daisy is an assistant professor of mechanical engineering at the University of Alaska, Fairbanks. She received her PhD in mechanical engineering from UAF in 2013. Dr. Daisy's research is on rural energy in the Arctic, and before coming to UAF, she spent 7 years designing mechanical components for the semiconductor and power control industries in the Silicon Valley. Welcome, Dr. Daisy, and I turn it over to you now, and thank you very much for giving us a talk today.
Thank you for having me. How's the sound? Can you hear me okay?
Yes.
Yep, sounds great.
All right, so this is a little different from usual because usually on Zoom calls you can see everybody that's out there, but this will be like a black box. So anyone who's listening and watching, thank you for joining. Please feel free to ask questions as they come up. Usually it's better to stay on topic when we're on the topic and ask the question right then and there, and then it will be on everybody else's minds too. If you wait until the end, it's usually, sometimes you lose your momentum. So here we are, and I'm going to talk about rural energy. So a lot of you know this, but I'm going to give some background. So Alaska, we have basically every type of energy available that is used anywhere on utility scale, but we paradoxically pay the highest power costs in the US. That includes both Anchorage and Fairbanks and the rural communities. We have a lot of oil, obviously we have natural gas, we have coal, we have wind, we have a good solar resource, which I'll talk about. We do have some geothermal, but it's not very hot. We have a lot of river, we have a lot of coastline, the most in the US. And so there's a lot of wave and tidal potential. And so all of these are being investigated one by one for how we can optimize them to give us a good energy generation mix and how to keep our communities sustainable. So before we get into anything technical, so I'm an engineer, I'm not really great with policy or legal issues or whatever, but we do need to talk about PCE because that is something that comes up and it impacts the drivers behind whether people want to develop a resource and what it will do for them financially. So power cost equalization was an endowment fund established in 1986. The idea is that the Fairbanks to Anchorage and down to Homer, we're all electrically connected. And so we benefit from each other's investments. So the state actually put a lot of money into big hydro projects and into that intertie. So that's why we in Fairbanks are able to purchase power from Anchorage's natural gas. But the rural communities are not connected to us. And so they didn't get to benefit from that, but they pay the same, inputs into Alaska. And so in order to equalize that, this endowment fund was set up. It's managed as a separate fund of the Alaska Energy Authority. And rural communities, about 29% of electricity sold is eligible. It's only for residential, and it's only for the first 500 kilowatt hours. The funding is renewed annually, so in theory, it could disappear any year, which was a threat last summer, but did not happen, thank God. But the result of PCE is that the cost of residential power in villages is set artificially, basically, not to profit the utility, but so what you do is you average the cost of power in the three big urban centers, so Anchorage, Fairbanks, and Juneau, average the three, and then add 10%. And that is the most that residential customers should pay for their first 500 kilowatt hours in PCE communities. So commercial entities like the store don't get the PCE rate. So the consequence of this is a lot of times, a community will invest in a renewable resource, like they'll put up a wind farm. And the residents will say, well, how come I'm not seeing any savings in my power bill? It's because the benefits of the wind farm, cleaner air, less diesel importation does not benefit them directly financially. So it's a little bit of a PR challenge, but so PCE is a big part of the conversation. That's why I needed to mention it. All right, so here's a starting point. This is a poster that's actually in our lab at the Alaska Center for Energy and Power. It is sort of an idealized future village in that sort of encapsulates what a microgrid is in an Alaskan sense. So here we have a transmission line from our wind farm, but to nowhere else. This is an islanded community. We have our residential loads. We have, I see an electric four-wheeler, which doesn't exist yet. We have rooftop solar. We have apparently an electric boat, which also does not exist yet, but again, the idealized village. We have commercial solar. We have flywheels to regulate frequency. We have battery storage to carry over our solar into the into evening after the sun goes down, maybe a few more hours. A tank farm, that's our diesel, hydroelectric, and we have a wind farm. This is quite the community. What a microgrid is technically is a community that can isolate itself. In our case, we're isolated by geography, not by choice. But in the lower 48, a community can microgrid if they disconnect from the main grid. But the main concept is every power source that they have to make their generation match their demand at all times. And this is not easy. This is why you need batteries and flywheels. And this is why it's really hard to be 100% renewable. Because your diesel you can control. You spin it up, you spin it down. You turn on more generators, you turn off some generators. The wind doesn't do that. Solar doesn't do that. Hydro does a little bit, but you can't control the long-term flux of the water. Seasonally, like summer to winter, your flows will change. But it is nice when the water is flowing. Then it's as good as diesel. You can control how much power you get out of it. Solar and wind, not so much. Hydrokinetic, not so much. But yeah, so today I hope to talk about microgrids in general. And then if we have time, I'll go into the individual technologies. So I'll start with solar and wind, and then I'll go on to these other hydro things. All right, so again, what do we mean by microgrid? The average production of the United States lower 48 grid is 500 million megawatts. This is the entire lower 48. The average production of the rail belt grid, which only goes from Fairbanks down to Homer, and as far as Delta Junction, we don't even make it past Delta Junction. We are 600 megawatts. So we're a lot smaller. And then aside from the rail belt grid, there are also 200 individual microgrids in the villages all over the place. So every one of them has to do their own management of load versus production. The average village, well, it's hard to say an average. There's a very large statistical distribution, but they range from about 50 kilowatts to about 400 kilowatts, with the exception of the hubs. So like Bethel, Nome, and Kotzebue, they're 3 to 5 megawatts each, and every single one is islanded. There are some interties, and there's an intertie from Tok part way down the Tok cutoff, and so it connects 3 other communities, but that's about it. So just to give you a sense of scale. And so this is why our definition of microgrid is different. So outside of Alaska, like federal government people who are interested in microgrids, when they say microgrid, they mean a small grid, which means tens of megawatts, which is huge by Alaska standards. So it's a small grid that can be operated in islanded mode. So that means it has to possess some of its own independent generation capability, and it has to balance with its own load. So it has to have some control structure, some control architecture. So by outside standards, the entire rail belt is actually a microgrid. But within Alaska, we don't call the rail belt a microgrid. We call it our main grid, and we call the communities microgrids. So our microgrids are even smaller. So on the scale of tens to hundreds of megawatts, they're islanded all the time, not by choice. So that's a distinction that people outside often don't understand. They say, oh, microgrid, yay, we can be islanded. But here it's like we're islanded all the time. So like people will fly up to a village to work on the power plant, and they'll say, okay, so we need to work on these generators now. Can you connect to the main grid and shut off the generator? And you're like, no, you can't do that. So that's a pretty big distinction. The other thing is we cannot turn off power ever. Like we have no risk tolerance. I know in tropical areas that are also sort of have, shall we say, immature electrical infrastructure, they have planned rolling brownouts. There are times when it's like, oh, you'll have no power between 2 and 4 p.m. And it's fine, just whatever, don't cook then. But here, you just can't do that because people would die. Like people depend on electricity for heat. So we're a lot less risk tolerant, and we have to have a lot more redundancy. Our power plants in general have capability maybe 5 to even as much as 10 times the load that we'll ever need. It's like if the peak load is 100 kilowatts, you have to have like 800 kilowatts of generation capability. So we can never at any time shut down an entire diesel fleet. So why is anyone besides us interested in microgrids? So here's another thing about doing research in Alaska is a lot of our problems are so uniquely Alaskan that nobody else wants to invest money in them. But microgrids are different. Everybody's interested in microgrids. And Alaska, because we are stuck in the microgridding world by circumstance, everybody looks to us because we've been the first generation of drivers. So for us, we have these microgrids because we have a very small population that's widely dispersed. Again, we have over 200 of them. And here's the interesting part is over 70 of them have some renewable generation. We have 12% of the renewably powered microgrids in the world. The reason we're so islanded is that it's just not economical to build transmission infrastructure for like thousands of miles just to serve 200 customers. That's just not economical. So each community here is islanded both electrically and they're not on the road system for the same reason. Nobody builds roads, for thousands of miles over permafrost and tundra and mountain passes for like 200 people. That's just not done. But in the rest of the world, microgrids are not required by circumstance. They're actually a strategy to capitalize on distributed energy generation. So now that the world is moving more and more to renewable, there's no longer one coal plant serving, millions of customers all over the place. It's just, well, there's still your coal plant, but then there's like a wind farm over there. There's a solar farm over there. There is a hydro resource over there. So now we have distributed energy. And you can capitalize on this better with microgridding architecture. Also to increase energy security, again, same thing, when you have more locally generated energy that you can produce for your own community, you can increase your local energy security. If there's, whatever political thing happens with Middle Eastern oil, you have your hydro producing for you, right? And it also is a hedge against the fluctuation in energy prices. Like once you invest in your wind farm, which can be very expensive, but after that, you know what your costs are. Like the cost of labor doesn't fluctuate as much as the cost of oil. So that's another reason to invest in renewables. And then also the final reason, and this is also of interest to like the military, they're big on this, is to increase the resilience of your grid, which means that, so like rolling blackouts have happened in the lower 48. Very famously, a few years ago, one happened all over the Northeast, which is a big deal because that's their big population center. Like New York was in the dark. But the idea is if you have islanding capability in your different load centers, if you can cut off from the grid, you can save your community from the rolling blackout. If there's an outage, the community down the road, and you cut off, like, okay, well, we will disconnect for a couple of hours, then you can be more, your community can be more resilient. And that's actually something that we're looking at with several different research projects. Like even within one community, if you can, in an emergency situation, like I'm looking at one project in Cordova, for example. So Cordova is a big fish processing community. It's on the ocean. And they are vulnerable to tsunamis. They don't happen very often, but that's one of those events that's like what they call low probability, high impact. So if a tsunami were to inundate town, the power grid would definitely be at risk. But if you can island, so the hospital has its own generation. Hospitals are required by federal law that they have their own diesel. So if the hospital disconnects from the grid, if you connect everything else that is critical infrastructure, like the Coast Guard station, maybe even some of the fish processing plants, if you want to save the fish, then they can island themselves even from the little Cordova grid and maybe preserve what they can, both of human life and economically. So different strategies like that. Microgridding is an area of active research. Are there any questions so far?
No, but I've got a question.
Okay.
So the question I had is, you said due to economic factors, hundreds or thousands of miles of grid for a small population doesn't make sense. Is there a cutoff point? Like, do we know the calculation for exactly how many customers you need to have to justify however many miles of grid?
That's really hard. Yeah, I don't know. You would have to ask an economist, but that's really hard to name because the cost of building a road varies a lot. Like going over a mountain range, going over permafrost is crazy. Like, I don't know what it's like in Anchorage, but in Fairbanks, we don't even have our roads all worked out. Like they have to be rebuilt every several years. So like going through permafrost even raises that cost per mile even more. I do know that when you build a new transmission line, approximately half the cost of that is building the road. So
okay, that's good to know.
If you have a road, connecting electrically is kind of, the barrier is way lowered. So it's easier to connect. But when there's no road, it's a lot. I know on Kodiak, which is mountainous, they have hydro, which is obviously up high, and the town center is down low. The transmission line from the hydro to the main town, actually there is no road. They put in each pole by helicopter.
Wow.
I know. You can look up pictures of that. It's crazy. All right. So in the last few slides, I kept blah blahing diesel this, diesel that, and people might be wondering why diesel. It's because in rural and isolated areas, it's really the most economical choice. So in Fairbanks, we can be base loaded by coal. We have a coal plant and we have a direct train line to Usabelli mine in Healy, but it's only because of that train line that the coal is economical. It is not economical to fill a boat with coal or to fill an airplane with coal. That just the energy density is not high enough. And then also like liquids. So diesel is a highly refined product and it's a liquid. So liquids are just easier to deal with. You can pour them with gravity. They're not, they don't need to be pressurized like a gas. You can carry them in a container. But with coal, anytime you have a solid, it's harder. You have to put an auger, you have to grind it. And it's also kind of still an unrefined product. Like it's not as energy dense. Diesel is very energy dense and you can ship it, the cost per kilowatt hour of energy is really low to ship diesel. And so that's why it's really the only option for isolated communities. So that's why like most rural communities are still on diesel and like remote operating bases usually, almost always is diesel. They try to offset a little, like there's a big diamond mine in Northern Canada where they put up 4 1 megawatt wind turbines and they offset like 10% of their diesel. And that's a lot of money, but still it's 90% diesel, it's just the only way you can have a backbone on your power production in a rural area. Diesel is also highly scalable. It can be very small or it can be very large. So just extreme examples. I just pulled Minto out of my imagination. Population of 210, their average load is 70 kilowatts, where like Oahu, which contains Honolulu, is their average load is 1 gigawatt. And they're also on diesel and they both work fine. Not fine from an environmental standpoint, but fine technically. So that's the main advantage of diesel. So again, Hawaii, like nobody's going to ship out a ship of coal. That's just not economical at all, but diesel is. So that's why diesel is the backbone, is our starting point. So when we talk about integrating renewables into a microgrid, usually the microgrid's backbone is diesel. So other places where diesel generation is used also share the same characteristics as Alaska and Hawaii. So they're remote, they're not connected to the main grid. So mines, other big industry, but mines is a classic example because they require a lot of power and they also, they are where they are, like the resources are where they are. So you can't move them. So you have to move your energy. So mines use a lot of diesel, military forward operating bases, remote research stations, so science stations, and then also backup power for critical infrastructure. So hospital and military bases, and then schools. Schools are in communities are often emergency gathering places and when there's a crisis, so they usually have their own diesel. All right, and so that's why the vastly predominant source of power in rural Alaska is isolated diesel generator sets. And as I said before, it's not one diesel, it's a fleet. So the other advantage of diesel, which I probably should have put as a bullet point, is unlike any renewable, diesel, you can control exactly how much you make. Like it can follow the load. At night when everyone's asleep, the load demand is very low. And in the morning when we wake up, start making coffee, toasting bread, the demand goes up, right? So in the course of a day, the demand on the grid goes up and down. And diesel is very nimble. It's a spinning thing, spin faster, spin slower, make more or less power. You can't do that with solar and wind. Like they don't follow what you want them to do. And so you always have to have some diesel. Like it's really hard to be 100% renewable. The only exceptions are hydro. So Cordova actually is very often diesel off because they have hydro. Kodiak Island is famously 100% renewable because they have hydro. They have the hydro that can balance the wind. So hydropower can actually do the same thing that diesel can do because it's also, you know where your water is coming from and you can predict how much hydropower you'll have available. And so you can also compensate for grid fluctuations. Okay, so hydro can be a backbone. And then Utqiagvik up north, they are less concerned about diesel. They don't use diesel at all because they have a long-term contract with the North Slope companies and they get inexpensive natural gas power. And then of course the rail belt, we're a different situation since we're connected to each other and we're connected to Usabelli mine. So Fairbanks has coal and then Anchorage also has natural gas in Cook Inlet. And we buy a lot of natural gas from you guys via the intertie. Thank you. So characteristics of rural Alaskan powerhouses is number one, the base load is powered by diesel. Two, more than one generator carries the load. Three, there has to be sufficient redundancy to take a generator at a time offline for maintenance. And then how you dispatch the load among your generator fleet, you can decide based on different strategies. So different sized generators will have different efficiencies. And the other thing is generators tend to run at their most efficient when they're fully loaded. It's like if you're running, so like, you know how a car gets maximum gas mileage when it's doing 50 miles an hour. So generators actually do their best when they're fully loaded, not when they're light loaded. And so what you want to do is maximize the load on each generator and not like half load all of them. So anyway, just different strategies like that. Or maybe like keep your biggest one as your base load and then run your smallest one to do your load following, things like that. But it depends on the situation. And then keeping in mind that the minimum acceptable load on a diesel generator is 20%. Any lower than 20 and it'll cool down too much, your lubricants will gum up, you'll actually cause mechanical damage. And your efficiency just goes completely to crap. Like generally efficiency starts dropping off when you go below 80, 70, 60 is kind of pushing it, but 20 is like the bare minimum. And some generator companies will tell you 30 is your minimum. So that's another challenge again with going 100% renewable. Cause like on a sunny day, you know, in the middle of summer when there's no rain forecasted for, you know, the next week, you might think, oh, we can go all diesel now, but like, we can go all solar now, but you can't just turn off your diesel because you never know when one cloud will go over your solar panel and then your diesel can't just spin up out of nowhere. It has to be running at its minimum, just flywheeling along at 20%. And that is just burning diesel for nothing. So again, balancing these things is hard. All right, so renewable energy then. Knowing about our backbone of diesel, we'll talk about renewable now. So renewable energy draws energy from the natural environment rather than of things that died 65 million years ago. And so that's why these things renew themselves in our lifetime. So the ultimate source of most renewables is the sun. It grows the biomass. Thermal changes between night and day ultimately drive the wind. Sun drives evaporation, which makes water flow. And renewables are growing rapidly. I teach this elective class called Energy in the Environment every 2 years. I'm actually teaching it right now. And it's interesting because I have these slides in the beginning, kind of like I'm giving to you guys. Oh, intro to renewables, yeah. Our energy generation mix that I present to them every year, it changes every time. Like every time. It's the most dynamic engineering class because I have to update my numbers every time I teach the class. These two numbers change approximately by 2 percentage points every 2 years. So 2 years ago, the US was 15% renewable, the world was 10% renewable. 2 years before that, you know, you can work your way backwards. But these numbers are growing every year. So that's kind of cool. You know, renewable energy is growing really fast. The reason for that is actually not warm fuzzies and saving the world and all this. I'm from Berkeley, so it's okay to make fun of myself, right? Like I'm always hoping that we're trying to save the world here, but actually those aren't the main drivers. Like the main drivers are actually economic and practical. So, which is actually a good thing because I think people are more reliable when they do things for money than when they do things for warm fuzzies. So now all the drivers are more practical, and so renewables are taking off in leaps and bounds. So for isolated rural grids, the main reason is not to depend on an external fuel supply, and also to keep your costs known. Once you install your renewable, you know what your costs are going to be, and you don't have to worry about the variability of the fuel supply or the availability. So like there have been times when a village, so the villages usually are located on rivers and they get their fuel barged in the summer. But if it's an unusually cold winter and a lot of people use the fuel for heating and they run out, then it has to be flown in on an airplane, which is way more expensive. And so renewables kind of hedge against that. They stabilize your costs at fixed values. They also have a more uniform distribution worldwide than fossil fuels. So there's pretty much some renewable energy resource everywhere. There's often government economic incentives. There's small environmental impacts, less greenhouse emissions, less pollution at the site, although manufacture of solar panels happens somewhere, right? And then finally, the last reason is to save the world. All right, so here is this chart I was telling you about. So this wedge here, this one grows by 2 percentage points every 2 years. So here's where we are. So you see renewable energy is still a very small slice, but it's growing really fast. Natural gas is actually also growing fast. It is cleaner than petroleum, but still has some emissions. And it's also way cheaper. Like the cost of natural gas has plummeted a lot, so it's growing. Coal is shrinking a lot just because of the pollution issue. So why is it only 2 percentage points a year and why is it still only 11%? There is a higher initial capital cost. And then the second two are actually the big ones. You just can't go too high a percentage when your renewable is intermittent and unpredictable. In Alaska, those impacts are amplified. We have even higher capital costs. The grid stability is an even bigger issue. So like on the lower 48 grid, if you were to dump on 10 megawatts of wind, like whatever, they wouldn't even feel it. That's so far beyond the decimal point. But here it's big. And so the more variable generation you add on a small grid, the more your diesel is really stressed out trying to follow this. And so that's a challenge. So yeah, they can't load follow. And also there's not a lot of local expertise. You know, installers, people to repair, they don't live here. They fly out from the lower 48 and each trip costs like $12,000 between transportation and lodging and their labor. All right, so we started at 11:45. All right, so we're halfway through our time. So, all right, so here are our primary renewables. And I want to talk about how different ways to integrate them to the grid. So all of them can make electric power. Oh, we have a chat.
Yeah, we do. I have a question in chat there. So WRT base loading, is there any consideration that occasional power outages can be accepted, allowing for the diesel plant to be shut down during the months in which the outages are highly unlikely?
So yeah, if you do have a scheduled maintenance that, well, there is no scheduled maintenance that requires turning off the whole plant. But if you foresee a catastrophe for some reason, then in theory, yes, you could cut everyone's power in July, like no problem. But in winter, it's definitely illegal. In winter, you're not even allowed to cut off somebody's power for a lack of bill payment. Like you just cannot do that. But how exactly did you phrase your question? Is there any consideration that apparent? Yeah, no. So yeah, in the summer you technically can, but customer acceptance on that is terrible. I'm not sure, like every time the power even flickers a little bit, people call our local utility, even if it's bright day in the middle of July, like you don't even need the lights. They call our utility and tell them how terrible they are. So that's a problem. And then we have another question. You explained why our microgrid situation is different from other places. In light of that, how do you think our experience in Alaska can help those other places? Well, that's exactly why everyone looks at us. All the national labs, the DOE, they invest a lot in Alaska because they want to use our expertise. We are less risk tolerant. And so they basically use us as first test cases. But yeah, that's exactly why they're interested in us. I don't know, I'm not sure that, did I answer the question? Oh yeah, the other thing we have in common, or the other reason that other people find us interesting is that we have really harsh weather. So between the solar, like the big swing between summer and winter, and also our harsh weather, the thermal variation and the solar irradiation variation, they're both really hard on materials. Like plastics tend to crack, cracks in even metal and glass tend to propagate more here. And so basically if it survives here, it'll survive anywhere. So people like to test here. All right, so this seems kind of obvious, but people don't usually think about it when they take it for granted. But when we talk about power, we're usually talking about electrical power. But there are other forms of power, like traditional wind power was a mill grinding something, or a water pump. The US heavy industry regions in the Northeast, when this country was young, was all driven by river power. Like there were water wheels in the rivers that drove industry. But nowadays we use electrical power for almost everything. It's less efficient than using the power directly, but it is more economically valuable because you can send it anywhere. And it's fungible. Power made here is the same as power made there. You can buy it and sell it on the open market. And so that is what we are all interested in. So all the new renewable development is in making electrical power. Now, making electric heat is a funny thing. It's not really common in most of Alaska. I would say 95% of households, if not more, do not do electric heat. And the reason for that is our heat demand is so high, so high that we benefit more from burning things directly in our houses to take the heat right there, rather than burn it in a power plant over there and then burning it, boiling steam, having the steam spin a turbine, having the turbine spin a magnet, having the magnet make AC electricity, then sending AC electricity across town, and then turning it back into heat. Like the efficiency on all of that is like 32%, where the efficiency on burning a log right here in my house is like 90%. And so electric heat is just not economical, with the exception of when electricity is really cheap. So who has that? Communities that have hydro, and those are the only ones. So Juneau, Ketchikan, Cordova. But even there where it's economical, electric heat is not common. Like people like wood. People like their Toyos. We have a comment here. I know this is a big Anchorage audience, so you'll probably tell me different. Do you and your colleagues are advise others? In theory, we don't. So like the mission statement of ACEP, the Alaska Center for Energy and Power, is we are energy agnostic. So we'll do research in a community. And if it turns out that the best answer is not to do renewables and stay on diesel, then stay on diesel. We're not an advocacy organization. Yeah, that's all I'll say on that. Okay, so is electrical heat economical? It's rare, except, and now I hope you're wondering why I have wind and solar economical on microgrids. So here's the thing. right, so I told you that diesel cannot be light loaded, not below 20%. But let's say you're a small community and you put in a wind farm, okay? Well, wind varies a lot. So, you know, you've put up a Met tower for a year, you've gotten all this data, you're like, oh, okay, now I know what kind of wind turbines to buy, I know how much power they'll make, okay, yay, put in my wind turbines. But there are days when the wind blows stronger than you need. And your wind approaches the point where it takes over most of the grid and it's stressing out your diesel. So at that point, you actually have to curtail wind. And there's different ways to do that. The turbine manufacturers have ways to do that. Some of them are mechanical, like you actually rotate the blades to cut the angle of attack, and then it'll spin slower and you'll generate less electricity. Another way to do that is just, you can put a brake on the wind turbine and it'll spin slower. Or you can do it electronically, like just accept less power and just have it, you know, blow off the power. Or just dump it on a load bank, have like a big toaster, attach it to a big toaster to the wind turbine, have it heat that instead of dumping that excess energy on your grid. And solar, the same thing. You can curtail solar production when it's making more than you need. But when that happens, you wonder, don't you? You're like, I spent this much money on my wind turbine and now I'm just blowing off energy that's free. Like, why? So, so one thing people have been doing, and you can Google it. I'll put the name in the chat. The Shenanic Wind Group. They are based out of the Southwest. So Kongiganac, trying to think of other ones. Quigillingok. I think there's 4 of them. But they are, so there are 4 communities that all have wind. And they're isolated, of course. But what they did was they installed in several of their houses, starting with the elders' home, so they could benefit first. They're native communities, so they're elder honoring peoples. They put resistance stoves in these people's houses. And it's basically a big resistor, like the big toaster I was telling you about, embedded in a ceramic brick. And when there's excess wind that the grid cannot use for electricity, they heat up those bricks. So it gives space heating. And then it actually feeds the heat demand in the house based on a fan blowing over the brick. So when it's getting cold in the house, a fan will blow over the brick and heat up the house. When it's getting warmer in the house, turn off the fan, and then your brick just kind of sits there. It's hot thing. So that is the one circumstance that electric heat is actually economical, that it's actually economical to use wind and solar PV on a microgrid. That's when it's already installed, you've got the power anyway, then you might as well just burn it as heat. But other than that, if you install an extra turbine just for heat, the economics just don't work yet. Maybe one day turbines will become so cheap you could install them just to blow off heat, but not now. Solar PV, same thing, although the cost of PV is coming down. But the problem with saying, oh, PV is cheap now, we can use that for heat, is that solar PV is out of phase with heat. It's like the most solar power is at noon and the most heat demand is at night. So it doesn't work very well. All right, so that's economic heat. Which can you use for direct heat? Well, those are more obvious. Oh, we have a chat. Just to clarify, wondering if you and your ASAP microgrid colleagues are advised. Oh yeah, we have partnerships outside all the time. We have partnerships with all the national labs. We have, and we work with other universities too. We work a lot with other people that are islanded. So like Hawaii, we have a partnership, and we have partnerships in Guam. Direct drive power seems like it could be good for islanded power grids. Yes. Wait, I was thinking direct drive wind turbines. You're thinking direct drive power. I'm not sure what you mean by that. If you want, you can just unmute yourself and talk. That's okay.
Well, that's from our YouTube live audience. That's not really an option there, but hopefully they can clarify.
Oh, okay.
Yeah, I'm not. That's kind of my question too. Is what's meant by direct drive power?
Yeah, I don't know if you could, whoever that was, if you could clarify. Oh, do you mean direct current? So that way we don't have to use rectifiers and inverters and all that?
Yeah, it could be. We got that 30-second delay, so.
Oh, okay. Well, all right. Well, I'll just keep talking about my chart then until we get that response.
All right, thank you.
Okay. Okay, and then which resources can you use directly to heat your home? Obviously, biomass is a big one. Oh, the chat's happening again. What I mean is having something directly powered by a windmill or dam. Oh yeah, such as fabric production facility or machine shop. So that, again, the efficiencies would be way higher, but the problem is the economics aren't there. Like if I'm a wind turbine company and I can sell wind turbines to the entire world versus sell, you know, a windmill to only communities that have a demand for that kind of power, then that really reduces it. But I could see that happening on a hobby scale. Like people that are wind hobbyists, they build all kinds of things, and that's definitely feasible, but the economics aren't there.
Is there an environmental impact for wind power that needs to be considered, like depending on the location or just at a federal level?
Oh yeah, there's a lot. So obviously the number one thing that people worry about is bat and bird deaths. But there have been, well, first of all, that has changed over time. Like the wind turbines that were first developed in the 1970s were a lot smaller and a lot faster. Now they're really big and the rotational rate is really slow. And so bat and bird deaths have gone down a lot. But there's still a lot and it's not trivial. But the numbers of how many are killed by wind turbines versus how many are killed by coal pollution and destruction of habitat and coal mines, that is, you know, another point of comparison. But the bigger thing is the number one killer of birds in this, at least in this country, is actually outdoor house cats. So actually by an order of like 100, it's like 100 more birds are killed each year by house cats than are killed by wind turbines. So, you know, when you're talking about wind as an environmental hazard, like usually the benefits outweigh the hazards, with the exception of very particular situations. Like if there's an endangered species that only lives right there, then definitely don't put your wind farm right there. But in terms of raw numbers, things are pretty good for wind. And then other environmental concerns, well, there's like a, what's the word I want? Like an easement around a wind farm. You can't build it too close to where people live. In the winter time, you know, in places that get cold, ice accumulates on the leading edge of the blade and it can get slung off, and that can actually be a hazard. You know, it can kill people, it could crush a car. And then another thing is noise. It's like it makes a noise that some people don't like. So that's another reason you have an easement. And then there's also a thing where like during certain times of day, the sun comes through and it flashes every time the turbine passes in front of the sun. And that's a nuisance. So you can't be near homes for that reason too. But those are the main environmental concerns. Okay, so, all right, so renewables to direct heat, only biomass, geothermal, and solar thermal. And then which can baseload? Only hydropower and biomass and geothermal can do that. They can load follow. So geothermal actually is not big in Alaska. We have a lot for recreational purposes, like sitting in a hot tub. Chena Hot Springs actually gets some power based on, so their geothermal is not hot enough to boil water. So they have this thing called an organic Rankine cycle where they boil a refrigerant instead, which has a lower boiling point than water. But the efficiency on that is very low. Like they still have to back up with diesel. So we don't have a real geothermal resource. But for places that do, like Iceland, they can boil water and they can make electricity out of their geothermal. So they can base load with geothermal. Biomass is basically operationally the same as coal. You burn it, you make steam. We don't do that in Alaska, although Fairbanks did in its early days. Like when it was a mining town, there was an entire wood-fired power plant. And then these last four: ocean tidal current, ocean wave, ocean thermal, hydrokinetic. So hydrokinetic is an in-river turbine that's like an egg beater. So there's no dam, there's no impoundment. It just spins with the flow of the current. These four are under active research. The last one in particular by ASAP, not me personally, my coworker Jeremy heads that up. One of these has been installed in Igiagig. One was tested in Ruby, one was tested in Eagle. But yeah, this is actually the one that's coming closest to deployment. These other three are very young, so we don't know. But in theory, any one of them, I think, could be run reliably, 24 hours a day. And then they could also base load. But anyway, those are our main renewables. Okay, so we are down to our last 15 minutes, so I'm just gonna kind of gloss over some of these. If you want, I can email you the slides and then people can review them at their leisure. I'm sure you will, it's so exciting. I'm sure you'll read this tonight, like with your dinner date. All right, so here are our average energy fluxes. And the point of this is that like traditional conventional power generation has a way higher energy generation per footprint than renewables. So that's another barrier to renewable development. And that's another reason why, even though the cost of solar is dropping so much, wind is still growing quickly, even though the cost is not dropping as much as solar, because the cost per footprint on wind is higher than the cost per footprint on solar. So renewable energy takes a lot more land space. All right, so solar energy costs are dropping a lot. I'm sure everyone has made this observation with their own eyes, like there are panels just appearing right and left. And so now it's within the grasp of individual homeowners, and that's why that's growing quickly. But I wanted to talk, so yeah, solar is growing quickly. So here, this green one is the cost per installed watt, and this yellow one is the installed wattage worldwide. So you can see it's been growing in leaps and bounds. Exponential growth has been linear, so it's growing. I mean, it's linear on a semi-log scale, so it's been an exponential growth. But what I wanted to talk about is why solar even works in Alaska, which usually makes people laugh their butts off. Since again, our peak load does not match our peak demand. But here is the first solar farm in Alaska. It's GVEA, put it up in Fairbanks. And the reason that this works is that the cost of solar has come down so low that it even works near the Arctic Circle. It's come down so much that it's economical even if you're only producing power in summer. And that was never true before. And the other thing is the other barriers to solar installation, like the fact that trackers would freeze. Well, guess what? We don't need trackers anymore because the cost of panels has come down so much. You can just put a panel facing every direction and no panel has to rotate. So all these things have brought the cost down, the cost down so much that in the Northwest Arctic borough, they only have 10% capacity factor, which means a 300 watt panel only makes average 30 watts. And that's fine. The payback is still about 10 years. And even the cost of installation was not as ridiculously high as outside. So there's a message in the chat, which I'll look at. Are there any nuclear technologies which are small enough? Not really. The smallest one that's still researched but not been built is, I think, on the order of 10 megawatts. Although next time you're bored, you can Google Galena nuclear. At one point, Toshiba actually had a small so-called micronuclear that they were going to put in Galena. It turned out to be a terrible project just from a regulatory perspective. Like nobody wanted a nuclear plant in Galena. And now there's no longer a military base there, so they don't even have the demand. But it's sort of interesting history.
How long are those panels supposed to last, the solar array on the slide that you have right now?
So unlike almost every other consumer product, they outlast their projections. So they're supposed to last between 20 and 25 years. And as far as we know, they're lasting forever. Like there's ones out in space, right, that are still doing fine. I suspect, although the industry is not old enough yet, I suspect that they will obsolesce before they break. I think in 20 years, people will be like, wow, look at this new solar panel that's 50% more efficient. Let's just buy that. And it'll be so cheap, it'll be economical to do that. So yeah, speaking of cost dropping, so now we're down to, so the cost outside to install a solar panel is between $1 and $2 per installed watt. And at the time, it was $5 to $7 per installed watt. And this is only 2014. So in 6 years, costs have come down fivefold. And at the time, so it was $5,000 to $7,000 per installed watt, and or five to seven per watt, or 5,000 to 7,000 per kilowatt. The cost of the Northwest Arctic borough averaged $82.50 per installed kilowatt. So like, think about a gallon of milk in the Northwest Arctic borough is like $20. So that's like 6x the cost outside. And here it's not even 1.5 the cost outside. So that was really impressive. Okay, again, and then solar actually is really good for the Arctic for other reasons. So there's no moving parts, which tend to fail, especially in the cold. They tend to ice up. They last for a long time. PV is also more effective at lower temperatures, just as a consequence of the physics. It's like any of you are electrical engineers, you'll know that resistance goes down in the cold. So PV capitalizes on that. We also have really clear air. So Fairbanks' strongest solar resource is not even in June, it's in March. And that's because our air is so clear then, there's no dust, there's no dirt, and we also get reflectivity off the snow. And yeah, PV panels are really robust. So far of all the rural installations, the #1 failure mode of a PV panel is feral children firing BB guns at them. They have not failed by any other means. So again, we don't need to pay for trackers. You just put them in a circle. And the other advantage of this circular array is, imagine at the Arctic Circle in the summertime, the sun never goes down, right? It just moves in a circle. And so you have constant solar production all day. And now your diesel is not stressed out at all. It's like, yay, nice power all day. All right, so you see the solar resource of Alaska is not as great as the lower 48. So here we have, this is color scale. The solar resource is the best in red, the poorest in this blue purple. Probably no surprises here, not that great in Seattle, really good in Arizona, New Mexico. But you see we're the same color as Germany. And Germany has the most installed renewables in the world between wind and solar. But the reason Germany was able to do that is they were incentivized by their government. So here's some fantastic numbers for Germany. They had the highest instantaneous penetration record in 2014. But what happened was their government actually incentivized renewables. They actually set goals for themselves of how much renewable generation they wanted within the next decade, within the next 50 years. And so they set these feed-in tariffs, which is where the government guarantees renewable energy producers that they'll pay a set amount for the electricity. And so now the power producers are like, yeah, we have a guaranteed market. And so they just went nuts installing lots of renewables. And then manufacturers of renewables went nuts responding to that, and prices came down a lot because they were able to build in mass. And so based on that, we can basically, everyone else in the world can thank Germany for kicking that off. And so now the cost of solar and wind in terms of per watt installed have actually reached parity with coal. So this is where we are now. But it's not as warm and fuzzy as you think, because like one side effect was that Germany also wanted to divest from nuclear at the same time. And so they switched their base loading from nuclear to coal. So now they actually might have more air pollution. I don't know. And the other thing, just to poke another hole in the warm fuzzy, is Germany is still connected to the main European grid, and they're still base loaded by France, which is still nuclear. So I don't know. You could say that net, they have the highest renewable in the world, but when they're able to buy and sell across their international border, it's not as difficult for them to manage. So their challenges are not the same as ours. Does that make sense?
Yeah, it makes sense to me.
Okay. All right, so it looks like I'll have time to talk briefly about wind, and then I'll have to save all those crazy turbines for you to think about on your own time. So here's the wind farm in Kotzebue. Kotzebue was one of the earliest deployers of wind. And their wind farm actually is a little graveyard of all these early experimental designs, but the only ones left now are these standard 3-blade, nice run-of-the-mill turbines. So wind resource is actually classified by class 1 through 7. And it's not just your average annual wind speed. It also captures qualitative things like what percentage of the time your wind is laminar, and what percentage of the time it's turbulent when it's no good for producing energy. So things like that. In general, they say, they say that the minimum wind power class to make it economical is 4. But again, that could come down now as prices are coming down. But anyway, so here we have a wind resource map of the nation and Alaska. Again, probably no surprise. The Great Plains have a really nice wind resource. We have great wind resources on the west. So here's Kotzebue and Nome, they have wind. Here is the Shinnik Wind Group villages. They have wind, of course. Out here is Gamble and Savunga. They're also bright purple. We're not that great in the interior, but obviously New Healy is pretty nice. Fire Island is actually not that great, but it's good enough to make it economical. Here is zoomed in on Alaska. So again, you can see our best wind resources are in islanded communities. So that's why they're harder to exploit. Because if your load is only like 200 kilowatts, it's hard to justify installing a turbine just for that one little community. But anyway, yeah, here we are. Can you even see Fire Island? No, it's a teeny little thing off Anchorage, but yeah, that's where you guys are getting some of your power. And I guess consequently also us, because we buy from you. All right, so wind resource is harder than solar resource for two reasons. One, there's it's not really predictable on the small scale. Solar, yeah, it's going to be sunnier at noon than at midnight. Okay, it might be cloudy, but at least you know that general pattern. Wind, you don't even have that. And it's really easy to anecdotally think you have a nice wind resource. You're like, oh, every time I go there, I lose my hat. But it's like, it's harder to pin down whether that is a good resource to exploit for energy. And so it's generally better to put up an anemometer. So on a tower, it's that little spinning cup thing, and you have it measure your wind resource for a year. And at the end of the year, then you can actually look and evaluate whether you had a good resource. And this is one thing of what the data can give you. So like here's a wind rose, and it tells you what percentage of the time the wind spends coming from each direction. It's like, the one on the right is a really nice resource. You can point your farm oriented that way. The one on the left, not so good. So that kind of thing. And then you get also average annual speed, and like what kind of turbine you can invest in, that kind of thing. There's also wake effects. So again, knowing the direction of your predominant wind. So turbine manufacturers will actually give you a recommended spacing in a farm, but they're usually optimistic. For some reason, they encourage you to buy more turbines. They tell you you can put more turbines in that space, but you lose a lot of efficiency in the back, as you can see. That's a model. It's not a real picture. Okay, and then we only have 3 minutes left, so I wonder if I should just quit here and see if there's more questions, or if I should just see if I can run through more damn slides. Don't you feel sorry for my students? They're stuck with me all the time. Anyway.
Yeah, no, it looks like we don't have any other questions online, so go ahead.
Okay. All right, so here is a nice damn slide that I assembled for you. Okay, so there's two kinds of hydropower that are, so this kind of hydropower where there's a dam and an impoundment and water flowing through a turbine. This is as old as, the 1930s. The Colorado River has a lot of these. And this is really nice, it can base load, but it's not really renewable. It's definitely carbon neutral. It's like when you cure concrete, it emits a lot of CO2, which is not as bad as a coal plant because it's not a human health problem. Like it won't cause lung cancer, but it will definitely be a climate change problem. And the other thing is all the water impounded is habitat destruction. So conventional hydropower is not regarded as renewable even by some governments. And so that's why people are looking at hydrokinetic, which actually does not impound any water, and you just stick this turbine in the river. So this is outside of Eagle that this turbine was being tested. So this conventional hydropower is a really large chunk of our so-called renewable portfolio. But I don't know how long it will continue to grow because of the other concerns. But I don't know, I'm not a prognosticator, but it's not really fully renewable. So that's why these other renewables are really growing. Oh, the other thing about hydropower is it's really cheap. I mean, it's really expensive installing it, but over the lifetime of the project, which can be 50, 70 years, the cost per installed kilowatt over the entire life of the project can come down to like 4 cents a kilowatt hour. So it's really economical, and there's no like lung cancer kind of pollution, although there's still CO2. And so that's why there's a lot of hydropower. Run of the river, I just talked about. So this is an area of active research. These don't all look the same as each other, these turbines. Send all of your slides for inclusion in the recorded session. Okay, great. I will definitely do that. So hydrokinetic is kind of where wind was in the 1970s. Like there's all kinds of different designs, and we don't know which one will come out on top. So they're all being tested now. And if you're interested, if you go to our website here, we actually have a hydrokinetic center, and you can go see all the different designs that they have tested. And now we are at time. So I'll quit there. Yeah, there's other.
So much more.
Yeah, I know there's other turbine pictures, but those are the main things. So. Whew.
Awesome. Well, thank you so much for your time today and answering our questions and giving us this very informative presentation, sharing your expertise, and I hope you have a great weekend.
Thanks, you do too. Bye.
All right, bye. All right, the password for today is energy for today's survey, and I will go ahead and share that on the screen.